All right, so before I do are there any questions? Let's talk about the problem we were doing on Monday. This should just be a repeat of what we had done. We have conservation of energy because the non-conservative force of tension is acting perpendicular to the motion, so it doesn't do any work. And so it has a radius of L, the length of the string, until it gets to here, and then the radius becomes L minus D. D is a reference to that length right there. So under conservation of energy, potential plus kinetic at point A is the same as at point B, and then there's no additional kinetic energy. I think yesterday we established H is equal to 0 down here, and so given that, we have this equation, which I'm pretty sure we had last time. The difference is, last time I think we kept L minus D into it, and now I'm just saying that's little r. I will tell you, the math is a whole lot simpler if we just let that equal r for now and substitute it back in later. So that was one of the issues that we ran into. All right, questions on this? Taking that last equation we had on the previous page and first multiplying by 2 to get rid of the fraction, and then isolating v squared, we get from conservation of energy, we get v squared is equal to this. Again, L is the length of the string, R is L minus D, so it's the radius after it hits the bottom. So L would be the distance from, in essence, the center of this to the center of this, center of mass. D is this distance right here. So L minus D is the radius, this radius. And then also using the centripetal motion, I have only one force acting on it at that point because the angle theta, hopping back briefly, that's the angle at which the tension drops off to 0 and it becomes a projectile motion problem. So weight's the only force acting on it, but because it is traveling in a circle at that point, that's sort of the final point where it is, there has to be some component, there has to be some force acting towards the center, and since that's the only force acting on it, it's weight times the sine of theta acting towards the center, and I'm pretty sure we had that last time also. Plugging into Newton's second law, the force is equal to mass times centripetal acceleration. We have a separate formula for v squared. Now, one thing I am doing here that I didn't do on Monday is I'm letting s equal sine theta just to reduce the amount of writing I have to do. Because as usual, the more writing I have to do, the more chances I have of making a mistake. Sorry if that's in your way. Questions up to here? So this should all be very similar to what we had yesterday. So v squared, we have two formulas of v squared, and I set them equal to each other. This is what we got from conservation of energy. This is what we got. This is what we got from centripetal motion. Get to here, cancel out, so set them equal to each other. I guess from here to here, I distributed to g, canceled out the g's, solve for this s, which is sine theta, and I get 2L minus 2R over 3. At this point, I went ahead and substituted in the value for R. R is L minus D. So plugging that in for R here, it eventually simplifies to 2D over 3L minus D. This might be different than what we had before.
No, so that's the same.
It's the same? Okay. All right, now the projectile motion piece of it. Using geometry, this is the angle theta that we defined on the first screen. And so this angle up here, it's being shot up at some speed v at an angle of theta prime, the complement of theta. I have, this is length here is R, which is L minus D. And so we can, from that, figure out that it is going to be going, I want to figure out basically information about what's going to take it for that mass to actually hit the bar. So the displacement in the horizontal direction will be L minus D times the cosine of theta, or as I've shortened it, RC. And for J hat, it's going to be going down, so negative RS. The velocity, or sorry, the speed is in that direction, so the velocity was going to be V times the cosine of theta prime, or V times the sine of theta. So that's why it's Vs. And the horizontal component, it's upwards, or vertical, as people say today. The vertical component is upwards. That'll be V times the cosine of theta. And I sort of broke it down here. Theta prime is that angle right there. So that means this angle up here is theta, so the opposite side is sine. And then accelerations. And that should come close to matching what we had before. We might have made some additional substitutions, but it turns out it's simpler if we don't plug the other stuff in quite yet. Questions to hear? So what I'm going, so far, our process yesterday was still spot on. We just got bogged down. I am going to deviate from what we did last time, where we found final velocity, vertical final velocity first, and then found displacement. But it should get you to the same place. There's nothing wrong with what we did yesterday, other than surely a careless error somewhere. All right. Plugging into that equation right there, because once it is launched, the string isn't doing anything significant. Air resistance, it's not going fast enough for that to be any significance. So my acceleration should be constant. And so plugging in the horizontal information, I have a formula for T. Plugging in the vertical information, I have this, and then substituting that in for T. And so this is the substitution there. These cancel out there. That's an R. And that leaves us with this, multiplying everything by S over R. I get rid of that R and I get a negative S squared. That S and R cancel out, and over here, one of the R's cancels out, one of the S's cancel out. So that's going to give us this. Adding S squared to both sides and adding this term to both sides, I get this. And cosine squared plus sine squared of an angle is 1. So that's why I have this equal to 1. So it's simplified very nicely down into this GRC squared over 2V squared S equals 1. Questions?
How does it simplify into cosine squared plus sine squared?
So from here, if I multiply everything, each term, I have 3 terms, each term by the sine of theta over R. Over here, the R cancels out, and I'm left with negative sine squared.
Oh no, I see that the equation up top.
Okay.
For some reason I looked at it, I thought that bottom one was saying that GRC squared over 2VS squared simplified.
Oh, no, it happens to equal that based upon this.
Yeah.
Okay.
I thought it was showing that it's simplified into that.
No, that would be impressive if that worked, but no, yeah, just for this particular problem. So I'm not quite, I see you're writing, so I'm not quite sure where you are in the.
I'm up there.
You're up there?
Yeah.
Should I give you a little bit more time?
I'll just write the answer.
So yesterday, yeah. All right, so this is where we left off in that previous screen. however you want to do it. If this fraction is equal to 1, then the numerator and denominator have to equal each other. Solving and then bringing back from previously, we had sine of theta is equal to 2d over 3r. This one we found a couple slides earlier. If the sine of theta is equal to this, and the sine of theta is also equal to the opposite over the hypotenuse, then I create a triangle here where my opposite side is 2d and my hypotenuse is 3r. This is something that we did not do last time, and to me, visually, it's a little bit clearer than what I forced last time. Using Pythagorean theorem, we can find this side has to be, so if that's 3r and that's 2d, this has to be, well, the hypotenuse squared minus that squared, square root. So that's a 3r quantity squared. Squaring this stuff, we get this. So cosine of theta would then be this length divided by the hypotenuse, which gives us this. So now plugging in for cosine squared and sine. We have this magical beast up here. That r is going to cancel out with one of the r's in the r squared denominator. Yeah, because it's cosine squared, so this whole thing is squared. And then I have an r on the right-hand side coming from sine, which will cancel out with the other r, so r's go away. That 3 is going to cancel out with part of that 9 right there, leaving a 3 behind. So we get this. And then multiply both sides by 3. So multiply that, we get this. Dramatic pause for questions. This is where we left off. So solving for v squared, we get this. And then bring it, but that's the same speed. This is the speed at point at B, at the point when the string starts to become slack. That should also be equal to the v squareds we've already found out. So I set that equal to RGS, which we had on slide 3. Setting them equal to each other, plugging in, that's the sign right there, which we just used. Getting rid of what we can, we come down to this. Cross multiplying or multiplying both sides by 4d, we get this. And then simplifying, we eventually get to here. This seems like a very simple expression. Now plugging our L minus D in for R again. And then I want to get all the D's together, because ultimately I want the ratio of D to L. And so there we go. So we end up with, it should hit the bar if the ratio of D to L is 0.464. So the question, does it actually work? It has in the past, we'll find out today. So first off, that is on tightly. Put a smaller mass on there, because our assumption was that it was a point mass. So now I need to figure out the length, and it looks like it's pivoting about the center of this, and I want to basically hit the center of mass of this, which is somewhere in the middle. So I just need to figure out what that is. I was thinking there were some meter sticks in here. Anyone see a meter stick? I have rulers.
I just run to the library real quick.
Yeah, well, I'm just going to leave that running, and some good video there. A mass just was swinging. of that. And in the middle here, 0.644. So L, 0.644 meters. So the bar D is equal to 0.464 times L, based on that. And if someone would be kind enough to do that calculation.
.2988.
0.2988
Yeah.
meters. So just shy of 30 centimeters. So let's go put it about there. All right, so. Somewhere around there. More. Too far. No, that's actually, that's. Pretty darn close. All right. Take your bets whether this is actually work or not. All right, I want that horizontal. Release. Pretty close. Didn't hear the clank I was expecting, but it just barely made it over.
Way too much.
Does it weigh too much? I don't think that's it. It's also possible that I wasn't holding it horizontally. Looked like it just kind of clipped it there, but anyway, the interrupted pendulum, I think for a physics demonstration, close enough. Not as satisfying as if we had worked it all out yesterday, but there it is. All right, any questions? All right, so chapter 7 was dealing with energy. Now let's shift topics. Chapter 8, momentum, and then we will bring energy back into it. Energy is nice in the fact that we don't really care about the vectors, other than the dot product, but energy and work are scalars, so it makes the math simpler in that respect. However, we do lose some information about direction, and so let's bring in momentum. If you recall, I started out this energy momentum section by having I have two objects coming together, and then they separate. So let's take a look at that. I'm going to start out with Newton's third law that they exert equal magnitude of force, but in opposite directions. That's the shorthand version. This is the force on object A from object B is equal to the negative of the force on B from A. We also had established that the two objects will touch each other for the same amount of time. And so we have force A on B times however much time they're touching. is equal to the negative of force on B from A times time. All right, Newton's second law. What is Newton's second law?
The logically emotional state of motion.
That's the first one.
Something's action will have equal and opposite reaction.
That's the third.
Force is equal to mass times acceleration.
That's the one. You could have just ported it out that one. All right, so that's the mass of A, because this is the force on A, it's the mass of A times the acceleration of A times time is equal to the negative mass of B times the acceleration of B times time. What is acceleration times time?
Distance.
What'd you say?
Distance.
Units wouldn't work out. What are the units of acceleration?
Meters per second squared.
And time?
Seconds.
So if I take meters per second squared times seconds, what do I get?
Velocity.
Velocity. Meters per second.
All right,